In this video, we're going to start talking about trends in the periodic table. And to do that, we need to discuss the effects that alter how the electrons are attracted to the nucleus and therefore change how they can interact with other materials. Most reactions are really the reorganization of electrons, moving them closer on or off, rebalancing how they're shared between atoms. And so the energetics of the electron orbitals plays a huge role in how easy it is to rearrange them. For our purposes, we're going to talk about just an atom, though. Let's talk about hydrogen. It has a nucleus, and then somewhere out here is its first energy level, n equals 1, and it has its electron. Now that electron is attracted to the nucleus. It sees one positive charge, and so the attractive force pulling in that electron is +1. The Z, the charge in the nucleus that the electron sees, is a +1 charge. But as we get more protons, which easier way to write that is just, let's talk about a helium nuclei with 2 pluses in its nucleus. Well, out here is still the n equals 1. If we think about the orbitals, the 1s, the 2s, the 2p, hydrogen only has 1 electron. Helium, 1s, 2s, 2p, it has 2 electrons, but they're going to go as low as possible. Remember, you can put 2 electrons per orbital, so they're both going to be down here where n equals 1. Well, they are both attracted to that nucleus. And so the charge in the nucleus is a +2. Now those electrons being near each other kind of repel. They want to push each other away. But remember that your 1s orbital is really all around our nucleus. So if our 2 pluses are there in the center, our electrons are taking up the entire volume around it. They can get away from each other. And so as far as each is concerned, it really sees those 2 pluses. Minimum interaction with each other, affecting each other by repelling. Problem is, what happens when you get to lithium? Lithium is a 3 plus. It's got its n equals 1, but it also has n equals 2 electrons. 1s, 2s, 2p, 1, 2, 3. Well, those electrons spread out. Kind of, again, showing them just near each other here for simplicity of drawing. Well, the 1n electrons, they see the full 3 plus. But the 2n electrons, they have to deal with the negatives that are in their way. Even if you try to draw it out a little bit, so we have our 1s here, and we have our 2s. Those electrons, they're gonna play interference. As far as the outside electron is concerned, while there are 3 positives, there are also some negatives in the way. The net effect is that, well, the 1s electrons on lithium see the full attractive force of the nucleus. The 2s electrons don't. We call them shielded. Shielding is when earlier n-value electrons block, effectively, some of the positive charge of the nucleus for the later n-value electrons. Those electrons in the 2s just don't see 3 full positives. Positives plus negatives will come out somewhere in between, and it sees those earlier electrons. It sees the negatives from them. Because the positives are concentrated and the negatives are spread out in a wave shape, it's not a 2 negative and 3 plus situation. Not exactly. But Surprisingly, it's fairly close. What we actually have is that for every element, we have a Z effective for an orbital. The Z effective is an approximation of what charge your outermost electron sees on its nucleus. So when I have my 3 plus, I have my n equals 1 with 2 electrons, and my n equals 2 with 1 electron. Well, there's a difference here. There are what we call core electrons, which are the earlier n values, and there are valence electrons, which are the outermost n value. This is important because only valence electrons actually can interact with other atoms, or at least effectively. If I've got a nucleus and then a bunch of electrons around it, spread out from some later element, and I have another atom come up and it has a bunch of electrons around it. Well, as these come together, they only get close enough for the outermost edges to interact. If you tried to push them further in, you'd have electron orbitals really messing up each other and pushing each other away, and so you can't sink super deep. Instead, what happens is your outermost electrons are the ones that interact. For the vast majority of chemistry, all the chemistry that occurs from those outermost electrons. So we are only really ever concerned about what the valence electrons are doing. They're the only ones that are going to interact with other atoms, and it's going to interact with the valence electrons on other atoms. And so, how strongly your valence electrons are attached, how good the positive attraction that keeps them on their nucleus is, determines how hard or how easy it is to move them around to make ions or to make new bonds. As a result, when we have the periodic table, hydrogen, lithium, sodium, potassium, etc., beryllium, magnesium, calcium, boron, carbon, aluminum, silicon, nitrogen, phosphorus. We're going to need a couple examples here. Oxygen, sulfur, fluorine, chlorine, neon, argon, helium. Boom. There we go. Hydrogen, we said, saw just the nucleus. Way back up here with hydrogen, its electron had nothing shielding, so it saw the full nuclear charge. Helium, same deal. The 2 electrons, both in the n equals 1, we don't consider them to interfere with each other. In fact, anything in the same shell, the same n value, we consider to not interfere with each other. There's actually a little bit of fine tweaking that we can talk about later that does come up, but for Z effective, it's assumed that things in the same n value don't shield. Well, hydrogen was a +1. Lithium, as far as its outside is concerned, there are 3 positives and 2 negatives for a total of 1 plus. It's not a perfect example, as we said, but for Z effective, we make the assumption. Your Z effective, your effective charge for your valence electron is equal to your protons minus your core electrons. So we had 3 protons, and we added the negative charges, but really this is just 3 minus 2 equals 1. As far as your valence electrons are concerned, there were 3 protons and there were 2 core electrons blocking it. When we get to beryllium, magnesium, and calcium, well, beryllium's got 4 positives. There's the n equals 1 with 2 electrons, and in n equals 2, there's also 2 electrons. This would be 1s, 2s, 2p. Beryllium has 4, so it would look like this. As a result, there are 4 positive charges. There are 2 negatives from the core for a +2. The outermost electrons in beryllium see +2 from its nucleus. That is how much charge it sees attracting and holding it in place. As we keep going on to boron over here. Well, boron would have 1 more electron. Boron's going to have +5 for its nucleus and 5 electrons. Now, we might be in the p's, but the s and the p's are all the same n value here. The 2. N equals 2 for 2s, n for 2p. These all are considered to not shield. So there are 5 positives, but only 2 core electrons from the 1s. So this is a 3+. Boron is a +3 for its Z effective. As we keep doing this and we add more electrons, say for carbon, well, that's going to be a +4 because it's going to have 6 positives for carbon for 6 protons, but only 2, not plus, minus, sorry, but only 2 core electrons for +4. The net effect is +5, +6, +7, +8. Helium is not +8, it's +2. Helium is out of place. It's thrown over on the right because it's a noble gas, but it really ought to fit right here over on the +2 column. So helium and hydrogen are kind of exceptions because they don't have anything except the 1s orbital. Well, that's great for boron and carbon and oxygen and fluorine and neon, but what about the rest of those columns? What about sodium? If I have sodium, it's element number 11. So there are 11 protons in its nucleus. It's then going to have its 1s, its 2s, its 2p, its 3s. Well, it has 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The outermost orbital on sodium, the highest n value, the highest shell, well, that's its valence, and that is the 3s. This is our valence. These are the electrons that will interact with other things. That valence sees a bunch of core. The n equals 1 and the n equals 2. All the earlier n values are core. So as far as sodium is concerned, there's 11 positives, but there are 10 electrons in the way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For a total of a 1+. It's just like lithium. As far as the outermost electrons, the valence electrons in sodium are concerned, they only see a +1 charge in the nucleus. They're not held on very tight. This is the same as we go for magnesium. It's going to be a +2. As we go to aluminum, it's going to be a +3. Silicon, +4. Phosphorus, sulfur, chlorine, they're the same down their column. The columns actually tell us the Z effective of all the things in that column. What do we expect the outermost electrons to behave like? How strongly are they attracted to their nucleus? How easy is it to remove them? How easy is it to share them? And such behaviors. Z effective is a handy tool to help us start relating things because things in columns tend to behave the same. As we'll see later, it is very determinant of charge and behavior. Lithium, sodium, and potassium all become +1 ions, and they're all very reactive. They give away their electrons really easily. Lithium, sodium, potassium, if you throw into water, lithium will fizzle on the surface, bubbling away as it makes hydrogen gas and becomes lithium plus. Sodium will catch fire and sizzle along the surface. I encourage you to go look up YouTube, alkali metals in water. Potassium, if you throw in water, just explodes. It's that violent a reaction. It gives away its electrons so easily that it actually is more violent than the sodium, which catches fire. And I remind you, it catches fire in water. And the lithium, which just reacts and fizzles. And if you keep going down, rubidium and the like, they explode even more. Cesium, incredibly destructive. Francium at the bottom, in theory, would be unbelievably destructive because they just are so readily able to give away their electron. They're not attracted to their nucleus very strongly. On the other hand, way over on the right, our neon, our argon, our krypton, our xenon, we do not expect these to give up electrons easily. The noble gases don't react. In fact, getting one of them to react won a Nobel Prize because for so long, nobody had ever been able to do it. Their electrons are so strongly attracted because they see such a big charge in the center that they don't want to leave. They don't want to go interact with other things. This is going to be the cornerstone of several of our ideas. Shells of electrons differentiate between core and valence. Valence is your outermost n value, your outermost shell. Core is all the earlier n values of electrons. Your valence is attracted to your nucleus, dependent on the number of protons and the number of core electrons shielding it. And this count resets every time we go back around the periodic table. Now, Z effective isn't just for valence. If we want to think about it for a second, we can find the Z effective for our 1s. There's 11 protons and no earlier n values for the 1s. So it just sees 11 positives. The Z effective for the 1s on sodium is 11 plus. We can also do this Z effective for the n equals 2. So for the 2s and 2p. Well, in this case, there's still 11 protons, but there are 2 earlier n value electrons, the 1s's. So the 2p and the 2s, they see a 9 plus for their effective charge. And as we said, the 3s, there's 11 protons, but it sees 10. Why do I keep writing plus? My apologies. But it sees 10 core electrons for only a 1 plus. Different shells are attracted with different strength, but it's the valence shell we usually care about because that is the one that is interacting. And since chemistry is about the interactions of things, we tend to care about those reactions, and so the periodic table is arranged to help reflect that.